Hello, I'm Renzo Huber, and I'm very happy to be here at this Gordon Research Conference, specifically because I love talking about the theme here, advancing beyond the limits of spatial and temporal resolutions. And I like to do this with respect to high-resolution fMRI. So based on the guidelines that were sent to us, I believe we should focus on talking about unpublished research. So I figured I talk about a story, the story of fMRI metrology. Because I think fMRI metrology is the really critical thing that allows us to keep advancing beyond the limits of spatial and temporal resolutions. And there has been a lot of advancements already in the past. In fact, I believe we have this Moore's law of fMRI resolution, where we get about an order of magnitude voxel volume reduction every decade or so. In the early 90s, people could do fMRI with these big voxels, hundreds of cubic millimeters. And then 2 decades later, people already could do 1 millimeter cubic. And now another 1.5 orders magnitude voxel volume reduction. We are 1.5 decades later. We can even see smaller voxels, right? And each different spatial scale here allows us to have a unique window into brain function. Like in the early decades of fMRI, we learned a lot about how the brain works by looking at these big structures, the brain areas, right? They are exciting things of the visual system, the sensory motor system, and uniquely human areas like for language. However, as much as the field learned about how the brain works by looking at these big structures only, it's kind of simplistic, and it is frustrating how little you learn sometimes by assuming that all the neurons in the entire brain area are doing the same thing, right? They're not. So as fMRI methods improved, people not only looked at brain areas, but also activity distributions within brain areas, namely along this cortical ribbon here. To do something like retinotopy, you could separate like vis-a-vis Kissick gyri, which helped a lot. However, it's still an oversimplification because you cannot be so naive to think that all the neurons across the cortical depth are doing the same thing. They're not, right? And with this latest resolution, we can actually try to look at different subpopulations of neurons across these different cortical layers. And this is very relevant because these different neurons, they do different things of neural computation. And importantly, they have different connections, which is relevant because the brain is ultimately a network organ. So if we want to understand the brain as a network organ that it is, we need to look at the connections, right? We need to look at the information flow across these connections. And therefore, we need to have access to these layers to see where information is coming in, where it's flowing out, and so on. And the big advancements in the history of fMRI method development to advance the resolution beyond the resolution limits is basically in the early decades it was focusing on hardware, on sequences and reconstruction, right? People went from 1.5 Tesla to 7 Tesla, from single channel birdcage coils to multi-channel arrays, from a single slice 2D EPI to now these very flexible 3D EPI methods, also using undersampling, right? A lot of things happened. They are giving us 2 orders of magnitude. But then what happened and what changed in the last 1.5 decades, right? We are still using the same old 7T. We are still using the same old multi-channel arrays, the same old 3D EPI with undersampling patterns. So I believe the big improvements in the last 1.5 decades was metrology. And I think it will play an important role also in the time as we move forward to the next order of magnitude of voxel volume reductions in the next decade. So metrology is the science of measurements. It's about calibrating your scanner. It's about configuring your scanner. Think of it like a scale, right? If you have a scale to weigh something, you need to calibrate it. You need to configure it. You have the hardware and software that need to be harmonized, and you need to have public standards, like something like a kilogram, right? And metrology is something we haven't really talked about a lot in the field of MRI, even though it's a big deal, right? Other scientific disciplines take this very seriously. There are these like billion-dollar heavy national institutions of metrology that we are not really taking advantage of so far. And they have amazing breakthroughs. They, like, for example, if you measure time very, very precisely, it can change the world. And these institutions, they tell us how to measure time very exactly, and these standards are being fulfilled in every GPS satellite now. And they are serious scientists. They are not kind of technicians that are just thinking about definitions. They have breakthroughs, they redefinitions of the kilogram by having very exact scales as well. And a number of these metrology institutions are actually reaching out to us, publishing in our journals and telling us, that we can be better scientists if we take advantage of their tools as well. So I would like to talk about metrology for fMRI, how to do calibration of your scanner, how to configure your scanner for fMRI, how you retune it, how to retrofit it for fMRI. We need public standards, and then we have the different components that we need to harmonize. And from components, we, for example, can think about sequences, right? Sequences is an established component in fMRI. It has its own journals, its own sessions at ISMRM. Then we have reconstruction, which is an established thing. And then we have the hardware, right? And for some of those components, we have standards and we have a kind of interface for them. Like the vendors find it useful for us to not only develop sequences, but then also to fine-tune, calibrate sequences for our purposes. For example, they give us something like IDEA. You can do sequence programming in that, or there's Pulsec even, open source, right? For Recon, it's the same, right? We have ICE. The vendors find it useful for us to give us access to that component to fine-tune it for research, and there are open source versions as well. However, for the hardware, there's no such thing. So how should we kind of combine these different components to harmonize them? For the hardware, I would like to use the same old hardware and then fine-tune it a bit, right? For my purposes of high-resolution fMRI. And this is where metrology comes in, and I think where it can break barriers of temporal and spatial resolution. So I would like to tell you 3 stories of how metrology can advance first, the temporal resolution. Let's start by temporal resolution, which is a big issue in layer fMRI because we have big matrix sizes in layer fMRI. We usually have matrix sizes in the range of 200 and 300. So just this single fully sampled image has about 13 million voxels. And it takes time to acquire 13 million voxels. In fact, if you're not undersampled, it takes about 41 seconds. And that's a problem, right? No neuroscientist is going to take this protocol. They will not even look at that. So if you do undersampling, you can see how we can go faster, right? From grappa 4, grappa 8, 12, 16, 20, 24, and so on. And then you can see that those data, they would be beyond the limits of temporal resolution, but those data are unusable, right? They're completely written with artifacts. And historically, this would be seen as a reconstruction problem for some reason. However, I think reconstruction is not the right solution here, right? If you look at the reconstruction literature, they would tell us, yeah, the limit of grappa is the chi factor. This does not look like chi factor to me in practice, right? The chi factor would be salt, pepper, noise amplification, random noise, right? However, when you look at this very carefully, we are not SNR limited. No, we are artifact limited. We have all these EPI issues there. It's just that grappa is very sensitive to these artifacts, and it's actually amplifying any miscalibration of your scanner. So basically, when you do grappa, you are unaliasing your images that have been acquired at the same time. So you are imposing aliasing patterns by acquiring them at the same time, and then you unalias them based on the coil sensitivities. This means, however, that when you have a small miscalibration, for example, here this flickering here, which is a residual aliasing, an erroneous aliasing, grappa is very confused by that, right? Because now you have erroneous aliasing based on your known aliasing, and then when you unalias them, grappa is very confused. And then it cannot do a good job. So a small error in the base image results in huge error after you do heavy grappa, right? So all we need to do in order to unlock this new temporal resolution domain is not to have better chi factors. No, it's to have better scanner calibration. And these artifacts are kind of well described, and we learned about them also quite a bit in the last decade. So I would like to just show you a couple of them that are responsible for this image, why it's not useful. For example, let's start by talking about these shading patterns, these fuzzy ripples, we call them, low spatial frequency ghosts. And they are mostly coming from interactions of the gradients with the third order shims that most 7 Teslas are equipped with. And because these gradients, they have a certain symmetry with the third order shim wiring patterns, right? So they can have this mechanical inductive coupling. So when you want to play out an EPI and you look at it very carefully, you can see that the EPI is not perfect, right? We have these weird beat frequencies, these ringing effects from the mechanical resonances. So when you unplug your third order shim, because it doesn't really help much with respect to B0 homogeneity anyway, it's perfectly nice and clean. So basically disconnecting your third order shim allows you to get rid of these fuzzy ripples, and you get nice, smooth, and clean artifacts. But that's not the only thing we are limited by. You can also look at these edge ghosts, right? And they are coming from short-term eddy currents. And I guess everybody knows that when you want to play out a trapezoid like this, your scanner actually does something like that. And this is well known. So usually what you can do is you take your nominal gradient shape and you just shift it, which is happening in the tune-up of the scanner, and to measure this with a delay correction. This means, however, that we still have this issue at the corners there, which is less than half a millisecond. And eddy currents of this spatial scale are not even measured or configured in your pre-emphasis. So when you take your API in high resolution imaging, you see that we have this kind of asymptotic behavior here. We are having a huge gradient moment that we are actually missing. On top of that, we also have this ringing effect, which has a different purpose that we can solve by other means. So if you collaborate with your fellow metrologists from the vendors here, for example, we can just have one additional parameter in your pre-emphasis, the short-term eddy currents that are usually not considered, and then suddenly we can reduce the error of the gradient moment by an order of magnitude and then get very, very close. We still have this ringing that we can take care of later. And this helps us to really nicely get rid of these edge ghosts in highly accelerated images. And last but not least, we also have artifacts like these phase inconsistencies resulting in these weird interference patterns. And they are particularly relevant in high-resolution API because there we have very long echo trains, and it takes time to go back and forth and back and forth and back and forth in K-space in API. So any kind of phase error really accumulates along this path. So while the center of the K-space lines has a nice smooth phase evolution, so we have quote-unquote just distortions, it's much more problematic in the periphery, where we have these odd-even chumps. And they're problematic because there we have ghosting of them. And this is a specific case for metrology, where we can try to harmonize the reconstruction with the hardware imperfections. So for example, you can take advantage of the linearity of the Fourier transform, namely by knowing that if you invert the read polarity, the sum of those two images must be the same as the sum of those two images, right? So, and those two images would have a nice smooth phase evolution there. So in practice, what you can do is you do an additional calibration there, where you play out the opposing read polarity, where you do see these artifacts, and the artifacts are always there, right? They just have the completely opposite phase, 180 degrees shifted, and so you can characterize them and calibrate them away. And you can even do this in a temporal specific fashion, for example, in this software here. So with all these different metrology tricks to fine-tune your scanner for high-resolution fMRI, you can turn those kind of data into those kind of data, where you certainly can easily go to grappa 16, maybe even grappa 20, where you're then finally limited by the thermal limit of the G factor. So with a bit of metrology, you can break barriers of temporal resolution by an order of magnitude and do whole brain layer dependent fMRI in these temporal scales that are relevant for neuroscientists. As a completely alternative approach, if you don't have access to all the scanner reconfigurations from your vendor, you can also build your own metrology device. And I think the ultimate metrology device is the AC/DC coil from Jason, which can do a lot of calibration and fine-tune anything you want for fMRI purposes. And that coil has been originally developed for B0 shimming, which is published already, so I will not talk about it, but I will talk about the exciting new stuff, namely to not only look at static B0 shimming, but then also to use very short-term field imperfection calibration. And this is a project from Hao-Tian Hong, who also has a poster here, and you can see by the number of screens that he needs, he's managing quite a different number of systems. For example, when he doesn't touch the third order shim from the scanner, he gets data like this, right? And they are good data. People use those data a lot for high resolution fMRI, but they're not perfect, right? In some areas we have these interference patterns. So he can, when he plays out an auditory task, you can see that there are some parts that are nice, trustworthy, but other parts not so much. For example, here this dark spot. We don't have activity there, but does this mean that we actually can trust it that there's no activity there, or is it just because of the lower sensitivity? And then on the other side, we have these weird negative voxels here. Yes, we know that there could be inhibition, but is it inhibition? Can we trust it? In order to look at that, he takes scope to measure the EPI trajectory and compares it to the nominal trajectory. And then when you zoom in up there, you can again see this kind of oscillatory pattern of the beat frequency with the mechanical resonances. So instead of trying to mess with the scanner configuration, to take it out of configuration, retrofit it, and lose your FDA, you could rather play out the missing field with your AC/DC coil. In fact, you can play out fields up to, I think, 100 kilohertz. So you can not only correct for these slow oscillations, but you can also correct for the eddy currents and these GPA ringing and regulator artifacts as well. And as soon as he does that, you have a nice and clean, stable EPI, which then allows you to convert those kind of images in these beautiful images. And then when you do a functional activation task, you can see, oh, this was actually a true negative. There's no activity here. Now we can trust it. On the other side, we see that these negative voxels, they were actually false negative, right? False inhibition. And it was just an interaction of positive signal change that was destructively interfering as a ghost with the neighboring regions. So there's actually no such inhibition in this task. And as soon as you can trust these data, you can then also use them to better understand the neuroscience, the laminar pattern of the auditory network. And this is something that was done also by Kenju Koiso, who acquired a lot of data across these networks. For example, this auditory network, where we have this rather surprising result that these primary sensory areas, like the auditory network, is really dominated from superficial and deeper layers. The middle layer is usually the weakest one in resting state connectivity or naturalistic tasks. And that's not unique to the auditory cortex. We also see this in other primary sensory areas, like the visual network, where we have the strongest statistical scores in the superficial and deeper layers, not the middle one, which is something that maybe we can talk about also. And I would love to hear your thoughts on this. And this is unique to the primary sensory areas and not so much for the cognitive networks, like the default mode network, or particularly the parietal frontal network that is similar across different depths, or even has a slight dominance in the superficial layers for meso here. And those networks are particularly relevant because they might have implications for psychiatry. Because ultimately, psychiatry and like most psychiatric disorders are network disorders, because ultimately the brain is a network organ, right? And I would like to explain this with this little metaphor of a street network, right? So fMRI, conventional resolution fMRI, is very, very good at seeing networks, right? And it's also quite good at seeing these macro scale networks when they are disrupted. However, what fMRI is very, very bad at is understanding the mechanism, understanding why in this very specific patient the network is screwed up. So if we look at this in the metaphor of the street network, that's the Boston Street Network. I live over here, and there are different locations here. There's Martino Center. We have another 7T here in the radiology that I'm scanning sometimes, and we have the university campus over there. So when you just look at the correlation of my geolocation with GPS, you see that this is kind of this is the Renzo network. And then sometimes the network is disrupted, right? It's not due to, in the street network, it's not due to schizophrenia, but in this case, it's due to a traffic jam, right? So I cannot go to the Martino Center because there's something like a World Cup happening, and then all the bridges are kind of blocked. You can see that this network is disrupted by looking at my geolocation or just the correlation of the activity, but you don't really understand the mechanism of this traffic jam or how to fix it, right? Similarly, in conventional resolution fMRI, resting state fMRI, you see the network disruption, but you don't understand the mechanism. And you can try to look at this at a micro scale. In fact, electrophysiologists tell me that, well, fMRI is indirect, you need to look at the true neural activity, the micro scale, the neurons, everything comes down to the neurons ultimately. It's just kind of true, but it's still, I think, not the right scale to look at networks, right? Looking at networks by looking at neurons is like looking at traffic jams by looking at wheels, right? yes, the wheels are ultimately responsible for the traffic jams. If the wheels would just keep going, we wouldn't have a traffic jam. But it doesn't mean that we need more research on wheels in order to understand the traffic jam. No, we need a different spatial scale. We need this mesoscale. For example, what Google Maps gives us, namely it gives us these layers of the different connections, the lanes of the street, right? So you see, oh, the network is disrupted only in this direction, not the other direction. So I get better insights of the directionality of this network disruption. Similarly, in psychiatric disorders, where you can see that in the attention network across the layers, there are actually different subparts of the network that are differently affected, like the superficial layers as opposed to the deeper layers. They even come out as different ICAs in this resting state analyses. So we need this mesoscale to better understand networks. And I would like to show you one example of how we look at network disruptions by looking at the visual network, which is here a metaphor of the street network of the visual system in humans, where we have the retinal ganglion cells. The signal comes into the eyes, then to the visual cortex, which is mostly sensitive to brightness changes. It moves all the way up the hierarchy, maybe to something like V5, that's sensitive to motion perception. So basically the signal comes in here, then goes to V1, to V5, and so on. And we have this hierarchy with different stages where you do see that any input into any given brain area that is coming from something lower in the hierarchy enters into the middle cortical layers. So we know this hierarchy based on the laminar connectivity pattern. So if you move from the bottom up, it comes into the middle layers. However, the same brain area is receiving feedback input from another area that is higher in this hierarchy in the upper and or deeper layers. So by looking at the layer connectivity, we not only know if a brain area is involved in a certain task, but importantly, we know where this activity is coming from. If it's bottom up or top down. And we can try to disrupt our network to then see how the rewiring changes. For example, with Marco Barilari, we were looking at data from blind people in layer-dependent fMRI meso, as opposed to sighted people. So for sighted people, you can engage V5MT by looking at these moving dots that really engages this brain area. But also in sighted people, you can try to engage this area with auditory motion perception by having these speakers moving left, right, which also engages this network in a different way, though, as opposed to blind people. So when you look at the layer profiles in this area here, you can see that most of the blood volume changes, most of the input energy is really coming from the middle layer in sighted people, because it's kind of moving from the bottom up, right, from the eyes to V1 to V5. However, when you look at the auditory motion perception, we see that it's the feedback layers, the deeper layers that are being receiving input from the auditory motion perception areas and tell the visual system to shut down because they're not seeing anything moving. And this is completely the other way around for blind people, where in blind people we do see that in the visual motion perception area, V5, we have this inverted U shape. So for auditory people, they're kind of rewiring the brain, and suddenly these visual motion perception areas are being hijacked by auditory motion perception, seeing this rewiring. So in layer-dependent fMRI, you learn important information, not only if a brain area is involved in a given task, but then importantly, how it's differently involved, right? Where's this activity coming from? After talking about how to make layer fMRI fast enough for cognitive neuroscience, let's also talk about breaking barriers in the temporal resolution, and spatial resolution, excuse me. And this is particularly relevant as most of us are equipped to have these clinical scanners that are not really developed for high resolution fMRI. So we need to do a lot of metrology in order to kind of retrofit them and configure them rightly, which is something that is specifically of my concern as I'm involved in this MGP High Field Center, where we have 3 scanners available. We have one Neuroscience TeraX scanner, we have a medical TeraX scanner in the radiology department next to the patient beds, and then also we have this very specific dedicated TeraX Impulse scanner that currently looks like this, and hopefully in next month it will look something like that. And these scanners are all amazing, but they're really configured and calibrated for different things. And this is a problem for the TeraX scanners here, because they are kind of too generic, right? You have these body gradients. It's like as you see it in this metaphor. You have this all-round machine, like a luxury van that you can take grocery shopping, you can take it for your commute, to go to holidays and whatever. but it's not really fine-tuned for anything, right? Similarly for the clinical 70, it's the same device, right? But it needs to be bulky to have access to put patients in there for anything in any case you want to have, right? So this is a challenge for metrology, as you need to reconfigure those scanners for your specific purpose. And it feels a lot like taking an ambulance to the racetrack if you want to do layer-dependent fMRI with such a clinical 70. The specific challenge being that these are really powerful machines. We have amazing gradient amplifier power. However, as soon as you take an ambulance to a racetrack, it kind of gets unsafe, right? You're exceeding certain safety limits. Specifically, when you even want to use maybe 30% of these gradient performance to do layer-dependent fMRI, you are being reminded that you're too bulky. You have a body gradient, you would trigger PNS. It's not safe to really use a fraction of the power of these gradients. So all we need to do now as metrology is to basically better harmonize our sequences or the reconstruction to our given hardware safety constrictions. And I would like to explain how this works by looking at PNS. So when you have a gradient, a constant gradient, and then you slew it to a different gradient strength, like you would do in EPI, you would have a slew rate that is this boxcar over here. And then the PNS is ultimately a low-pass filtered version of this boxcar, right? At the beginning of slewing, that the nerves are not really perturbed, but if you do it long enough, then bam, after 200 microseconds, you're exceeding your PNS threshold, and you cannot run this protocol on the scanner, right? Which is a problem, because it really restricts our gradient performance. So instead of having these beautiful, huge gradient moments to go to high resolutions, we're kind of stuck with this. After 200 microseconds, we cannot continue to exceed, and we need to stuck at this lower bandwidth to be safe, right? So reducing our performance quite a bit. However, when you're a metrologist, you can try to harmonize the different components and realize that there are different epochs in this slew, right? We have this initial epoch where we are really hardware limited, as opposed to the later epoch where we are more PNS limited. So instead of using a linear slew, what you can do is slew as fast as you can with your hardware until you're at 99% of your predicted PNS, and then only continue to slew at a slew rate that keeps you just at about this steady state, right? So going from this slow increase that exceeds the PNS to something like fast increase and then slow allows you to increase to the same gradient strength in the same time, while not exceeding your PNS, still giving you this huge gradient moment. Which is the equivalent of having high resolution. So by doing this tuning step allows you to basically break the barriers in spatial resolution. So if we look at these elbows here, we can take these elbow shapes and then repeat them over and over again until it looks something like EPI. It's not like the regular EPI, and because now we have this kind of temporal asymmetry. However, the important thing is that the right part does not exceed PNS, whereas the left part does, even though it has less gradient power. And the frustrating thing about the conventional EPI is that these PNS exceeding time points are very sparse. So you're exceeding the PNS maybe at 5, maybe at 10% of your time, but still you cannot run any of the sequence, right? 100% of the sequence is forbidden, and you need to dumb down your sequence 100% of the time in order to not exceed PNS. Whereas in POPE, the PNS optimized pulses for EPI, you're only reducing your slew rate when you're actually limited by PNS. And this allows us to advance beyond the limits of spatial resolutions, to go to 0.35 millimeter isotropic, for example, to appreciate the different spatial scales that we are dealing with as we want to push across the different resolutions. For example, you have the big vessels, right? These centimeter vessels, the sinuses, but then you also have these leptomeningeal vessels in the range of millimeters that have very interesting dipole-dipole interactions and blooming effects with positive and negative interactions, until you get to the pio vessels, these few hundred micrometer vessels that are sitting on top of the cortex, perturbing the top part of the cortex signal. These dark spots over there, and only then you get into the cortex with these stripes, these kind of ascending veins, And then the fifth order of magnitude is then finally the weakest part that's responsible for maybe 10% of your overall signal, which is the part that we care about, namely these different layers here. And because this EPI, you can also look at this completely in 3D to basically follow these vessels to understand their impact on the gradient echo signals. And because this EPI, we can actually also take advantage of the underlying contrast. Basically, anything that's dark here is a vessel. So if we invert the contrast, everything that's bright is becoming a vessel. So you can pump this through these AI segmentation algorithms and then follow these vessels individually to see which blob is connected to what, which is relevant because we do see that specifically the arteries seem to be all connected to these negative activity plots, interestingly. And I actually really love how metrology that's being fine-tuning your scanner for fMRI allows you then to also benefit structural imaging, because these EPIs are gorgeous and they have this superpower of seeing vessels, and because of all the iron in there, to not only see the big vessels and the leptomeningeal vessels, but then also the pile vessels, and then most importantly these intracortical vessels as they're passing through the cortex or partly passing through the cortex. And these vessels are exciting to me because they give us an independent measure of cortical architecture, right? Instead of myelo and cyto architecture, we can look at the surfaces to look at these dark spots, the vessels, and then looking at when you look at the density of these vessels, you can see that different parts of the brain have different drainage demands, right? And that match nicely with the Brodmann areas, giving you an independent measure of looking at that whole brain architecture by looking at the angio architecture instead of only the cyto and myelo architecture. And of course, this can be done across brain areas. In the visual cortex here, we actually had to push the resolution a bit further, and because the visual cortex is so thin, so now having voxels that only contain about 700 neurons per voxel. And there's this huge, beautiful mess of variants at these spatial resolutions that is just waiting to be described and taken apart with the next decade of research, I guess. But you definitely see to some degree what was expected, namely the layers. Like for example, here you see different Nyquist sampled stripes. For example, we have this middle stripe, this middle layer, as opposed to the superficial and deeper layers. But then also you see how this is disrupted. Like, and the deeper layer is kind of disconnected sometimes. And then we have guys like this, right? That's not really the deeper layer, it's not really the mid layer. What about this guy? And here it helps to have this beautiful structure contrast in EPI, because you can follow this guy across the different slices and see that it's just activated there. So that's something we should not trust. That's just an ascending rain. On top of that, we have interesting features like these negative voxels that we are trying to wrap our head around. And this is something that Alessandra Pizzuti in our lab is interested specifically. So she's tracing them back to find that they're all connected to big arterial branches. So those are arteries, those are pile arteries that are dilating. And not only that, as you follow those arteries back all the way to the brainstem, you can see that those arteries are even negative at the brainstem, and most likely due to the velocity changes, and therefore resulting in negative board signal changes. So there's a lot to be discovered as you fine-tune your scanner with metrology tools to break barriers of the spatial resolution. Next, let's talk about other aspects of metrology to push barriers of SNR, which I think comes down to the part of metrology that we have kind of community standards to better understand SNR and the origins of SNR differences. So we have quite a big community of ultra-high field scanners, about 150 installations so far. And so we are right. I think we are right at the time where it makes sense to have these standards. And aside of maybe a handful of exceptions, some of those folks in the room, all those scanners have these two coils, right? The STX and the PTX Nova coils. And these coils, they emerged from an engineering challenge a couple of decades ago now to an FDA clinically approved product. But we have absolutely no standards among them. We have no idea what's even in them, right? Every center has these coils, but I don't know which one to use for fMRI. I don't care much about beam plus homogeneity. So which one do I use? The STX or the PTX coil, right? It looks like the PTX coil is actually bigger, but does this mean that it has more coverage, right? Nobody knows. We don't have public standards. and the receive side looks identical, but does this mean that it actually performs identical? Nobody knows, right? There's no standards, no metrology. So I tried to look into that by comparing many different coils on the same scanners and the same coils across different scanners. We covered them with MR or floor racks. This is MR visible to map out the size of the elements, as well as a CT scanned 6 of them here. And then you can see that they're quite different, right? They're different coils completely. So for the PTX, while the cover is bigger, that the active elements is actually much smaller, like 3 centimeter difference, specifically at the top. So there's less coverage in the PTX coil compared to the STX coil. Specifically, when you put your brain in there, you can see that for the STX coil, the bottom of the visual cortex is really outside the transmit field, whereas the apex for the motor cortex is outside the coil for the PTX side, right? So when you are interested, for example, in the bottom of the temporal lobe, just with the CP mode of the PTX coil, you can see that it gives you more performance with the PTX compared to STX. This does not mean, however, that the bottom part of the brain is always better with the PTX coil compared to the STX coil. As you see that the receive side is slightly deeper in the coil. So we have this central brightening, as always in 7T, and that's moving towards the front for the PTX coil. So meaning that the visual cortex, the cerebellum, is actually right in this part where you have this destructive interference for the cerebellum and the visual cortex for the PTX, not the STX coil. More relevantly then for fMRI, where we don't care as much about B1+, we care more about the noise in the receive elements, you can look at the noise correlation of the receive channels. And to get good standards, I asked all my friends, and I got the noise correlation matrices for all the different receive elements from 32 coils across the different continents. And I do see very consistent differences. And this is the average of these 32 coils, where you can see that for the PTX and STX, we have very different coil sensitivity correlation matrices. Specifically, we have these off diagonals, right? This grid there, which is actually significantly more coupled for all the PTX coils compared to the STX coils. And when you try to look back where these elements are coming from, you can see it's the lower row. So that element here has the same noise coupling as this element, as this element, as this element, right? And this might be, again, due to just the fact that they have different geometry, namely that the PTX coil has this additional hardware directly at the bottom of the lower receiver elements, which is not the case for the STX coil. So the transmit side might couple and result in the noise coupling in the lower row here, which has important implications for layer fMRI. For example, as you want to do fMRI in the ventral part of the brain, specifically because of this noise coupling, the PTX coil has like factor 2 higher G factors for some protocols as opposed to the STX coil. It has more problems of G factor in the top part here. And these kind of informations were highly relevant in order to do layer dependent fMRI in the hippocampus as well, where we were interested in these different layered structures here. So the hippocampus has different subfields, and importantly, it has the different drainage infrastructure. Like, for example, we have this vein over here that is draining specifically the subiculum at that part, and also CA1. However, we also have this vein, which is also draining CA1, but then also CA2, CA3, and so on. So it was not really clear to us if we can do layer-dependent fMRI, and then if we can do it with bold, and then what to trust in bold and what not to trust. So specifically with David Feinberg, but also on clinical scanners, we were looking at blood volume sensitive vaso, which is not sensitive to veins as opposed to gradient echo bold, where we do see that for the subiculum, you cannot trust the bold. It has this huge bias towards the inner surface, which is different for CA1, CA2, or CA3, where the bold is actually giving very similar performance as the vaso. So there we can trust the bold. It's not as limited by the vascular drainage infrastructure. So I talked about how we can break barriers by looking at metrology tools, but also metrology has issues. Specifically, it's not really considered as a research discipline, even though it should be. Other disciplines consider metrology as research. It's more considered to be kind of insider knowledge rather than having public standards, which is a problem. Like, I have manuscripts in preparation now where my vendor colleagues, they say, oh, you cannot publish this is proprietary. a lot of this stuff I talked about, I cannot publish, right? So instead I can try to be a whistleblower, and then I have this series of scanner hacks on my blog instead. And I need to have a specific toolbox to kind of even avoid gatekeeping from my center. Like, for example, when I was in Maastricht, I didn't even have access to the service patient, which has the data of the tune-ups. What I did have, however, was access to the reconstruction, because that's somewhat more established, so I could kind of include additional reconstruction binaries and wrote a functor that can basically stream data from the service patient, or any patient for that matter, as a series of QR codes, right? As soon as I have access to the screen, I don't need to have access to the hard drive. And there are these available apps already that can receive QR codes, and then, for example, here receive data directly from the scanner as QR code streams, where the bandwidth is quite horrible, but it allows me to basically circumvent and hack and get access to parts of the scanner that I wouldn't have if I don't have those passwords. Other issues in metrology are that we are not considered scientists, right? Very often we are considered the scanner janitor, kind of the service people, right? I get grants rejected because the reviewers say that I'm more of an enabler, right? I'm not really the visionary researcher and scientist that they want to fund. I might get grants rejected because they say, well, all these ISMRAM folks, they're just optimizing things, right? There's no real new insight and new innovations in there. And give you orders of magnitude of different spatial scale. It's so frustrating. However, there are advantages also to be a metrologist, namely, every center needs us, right? So the job market is not that bad. And you can actually try to be the researcher, even though you don't get credit for it. You can be the researcher that you want to be. Like when I was a kid and decided to become a researcher, I was inspired by those folks, right? Those are the adventurous researchers. They build stuff, they have insights, they have an exciting life. However, when I look at researchers in the hallway of my center, I see people that worry about scan time. I see people that spend all their day about bureaucracy, right? If you want to get access to data, you need to sign material transfer agreement, be added to the IRB. I see people that are frustrated because they have failed experiments because of artifacts, right? As a metrologist, you have no such things, right? You can be this guy. You don't worry about scan money, right? You're useful to the center. You just do your research by maintenance, right? That's your research. You book maintenance account, you book development accounts. You don't worry about bureaucracy, right? If you want to have data from someone, and they don't make you sign a material transfer agreement, they actually literally drag you to the scanner and want you to look at their data to figure out what's wrong with their data, right? So I do my research by people giving me their data instead of asking them for it. I don't have such things as failed experiments due to artifacts. Instead, I rather have successful artifact experiments. And if I have an artifact, I describe it, I publish it or tweet it, or however I can make people aware of it, and I even get credit for it, right? So it's fun to be a metrologist. In conclusion, metrology breaks barriers of spatial and temporal resolutions. It's about measuring, measuring time. Everybody can do it. However, if you do it very, very precisely, you can change the world. You give the world GPS, right? Similarly for fMRI metrology, everybody can lay out a trapezoid, right? And I showed you a lot of trapezoids in this presentation. But if you measure these trapezoids very, very precisely, you're lifting a curtain of a whole new world of mesoscale information that just waits to be discovered. We do have issues, and I guess the biggest open question is, we don't really have a tool for us. We don't have a framework. As a sequence developer, I would have IDEA or PulseSec. As a recon developer, I have ICE or BART or whatever. But as a scanner metrologist, if I want to fine-tune my scanner and tune it for my fMRI, I don't have such tool, right? And I think we really need that. With this, I want to pitch a mesoscale metrology event, for that matter, where we are particularly looking at the intersection of hardware, physiology, vendors, patients, and sequences. And this is on November 5th in honor of the arrival of our Impulse at the Martina Center. You can also join remotely if you cannot be in the area during that time.